Okay, so last time we were looking at open sets, and we noted that if you took the union of two open sets or the intersection of two open sets, then you've got another open set back. And we had a full proof of that with a nice diagram. And then once you know that if you can intersect two open sets, you get an open set, then you see that if you intersect just a few finitely many open sets, you get an open set, and the same for unions. If you take a union of finitely many open sets, you get an open set. But something strange happened when it came to infinitely many sets. It turned out that you could take a union of infinitely many open sets and still be open, and we proved that. So we looked at infinite unions, or countable unions, and we showed that a union of any sequence of open sets gave you another open set back again. And we proved that by a slightly different proof structure. Then we looked at intersections of infinitely many open sets, and we showed that, unfortunately, when you intersected infinitely many open sets, you might not be open anymore. And we looked at a specific example of that, where the open sets under consideration were the open interval from -1 over n up to 1 over n. And we showed that if you intersected all of those, with a bit of work, you could prove that the only point left was 0. And that gave you a single point set. So we proved that if you intersected all those intervals, what you had left was just 1 point, a single point set, rather. And we know that single point sets are not open, so that showed that if you intersected infinitely many open sets, you might no longer be open in the sort of limiting case. So that doesn't happen for unions, but it does happen for intersections. So it shows us the difference. There's a nice false proof around that intersections of infinitely many open sets are open. There's a false proof by induction. Because you can prove by induction that intersection of 1, intersection of 2, and intersection of 3, that shows that intersection of any number is still open. Therefore, the intersection of all of them should be open, but that's false. So you might want to look at that false proof by induction and see where it breaks down. You can use a similar false proof by induction to prove that all sets are finite, which they aren't, and so on. So there are quite a lot of things to watch out for there. Which brings us to closed sets. Now, the big thing to know about closed sets is that closed does not mean not open. We looked at when sets are open and when they're not open, and we understand that now. And now there's a new term called closed. Now, I've mentioned that open sets are particularly important when you're doing things like complex functions, complex analysis. So if you do complex functions next semester, you'll see open sets again, in which case it'll be helpful that you've already seen them before. But it's not a prerequisite, so it gets covered again. Open sets in the special case of the complex numbers, which is like r squared. So it's just a special case of the open sets we've been dealing with. But open sets aren't the only nice kind of sets that you need to work with. Sometimes you need to work with bounded sets. Sometimes you need to work with closed sets. And some of the best kind of sets are the ones which are closed and bounded. So let's have a look at what closed means. And closed has a very easy definition in terms of open. It means that the complement of the set is open. So it doesn't mean the set is not open. It means that the complement of the set has to be open. So you look at your set E, and you look at its complement, E complement, which is r to the d take away E, and you ask, is that set open? If that set open, then E is closed. And the converse is true as well. It's in if and only if. In fact, a set is open if and only if its complement is closed, and a set is closed if and only if its complement is open. So now there's loads and loads of examples available, because you take any open set you've already seen, take its complement, and that gives you a closed set. But those may not be the most natural examples of closed sets. We've called a lot of things closed already, so let's have a look at this. Closed D cells are closed, and closed balls are closed, and I'm not going to prove these in full detail. Let's just have a look at some examples. Let's have a look at a closed interval in R to the D for a start. That's a particular kind of D cell. So here's a closed, oops, let's have a black for the real line. So it goes off to infinity in both directions. Let's have a look at 0, 1. We've done this example pretty much before. So here's a closed interval 0, 1, a typical closed interval, and its complement looks like this. So here's, let's take A to be 0, 1 contained in the real line. So here's A, but here's a bit of A complement, and here's another bit of A complement, and let's show that goes off to infinity as well. The more information you can show clearly on your diagram, the better. Now, sufficiently convincing diagrams in 1 or 2 dimensions are good enough for this module most of the time. So we can look at that example and we can see clearly A complement has no non-interior points. So from the diagram, clearly nint of A complement is empty. Or you could argue it's a union of 2 open intervals, though not bounded open intervals. So A complement is open, hence A is closed. Notice that's not the same as, that's not what you would do to prove that A is not open. To show that A is not open, you'd be looking for non-interior points in A. To show that A is closed, you have to look at the complement of A and check there are no non-interior points. 2 completely different proofs. However, it turns out that there aren't very many sets which are both open and closed, but there are some. So we're going to have a look at the difference between closed and not open. We'll be looking at using lots of examples. So here's your first example of a closed set. It's a closed interval. It's closed because the complement is open. And I can do, you can do a similar thing in 2 dimensions. Again, in 2 dimensions, sufficiently convincing diagrams are good enough. So let's have a little 2-dimensional picture. Let's have a look at 1, 3 cross 1, 2. Not quite to scale, never mind, it'll do. Right, 1, 3 cross 1, 2. Let's move that down a bit. This is a typical closed 2 cell, so it had better be closed because we already called it closed. Well, let's have a quick sketch of it. 1, 3 cross 1, 2. It's going to include its boundary, whatever that means. So here's A. And A complement is everything else. Notice that A complement is not a rectangle. The complement of a rectangle is not a rectangle. This is a mistake that's been made by people in the past. So the complement, oh, let me use a completely different colour. Let's use red. So A complement doesn't have those boundary points in. So A complement is everything out here. Can't draw the whole of it because it's obviously massively infinite, but here's A complement. Let's show you what I can. I won't bother with all the dot dot dots this time. I'll leave it to your imagination that it goes off, obviously infinitely in all directions. So that's A complement out here. So A is the closed rectangle. It's a closed 2 cell, which is a rectangle. Closed 2 cell. That's a rectangle. Shown, shaded in blue, including the boundary. And a complement is shown in red, shaded in red, and the boundary of the rectangle is excluded. Excluded from a complement. So that makes nint of a complement clearly empty. Again, clearly from the diagram, because it's a sufficiently convincing diagram in 1 or 2 dimensions. So nint of a complement is empty. So a complement is open. And so A is closed. And that's how you would justify for specific examples how they're sort of open and closed. But in fact, unless you're asked to prove for a specific example, prove that this closed 2 cell is closed or something like that, you can normally quote this as a standard fact. So the fact that closed D cells are closed is in fact a standard fact you're now allowed to quote unless you're specifically asked to prove it in a question. So I'll put in bracket. I'll put in quotes because we call them closed before we define closed. Closed D cells and closed balls really are closed. As I say, with the usual rider, unless the question says prove that a closed D cell is closed, or prove that a closed ball in R to the D is closed. If it says that, you're not allowed to quote a result to prove itself. Right. Okay, now, finite subsets of R to the D are closed. Now you might say, because they're not open. No. First of all, the empty set is a finite subset of R to the D, and the empty set is open. It's also closed. The empty set counts as both an open set and a closed set, as we'll see in a minute. So watch out for that. Finite subsets of R to the D are closed. Well, note that, first of all, there's been some confusion in the past as to what a finite set is. It's not the same as bounded. Finite means only finitely many points. So that's different from bounded. A finite set has to be bounded, but bounded sets don't have to be finite. Bounded sets can have infinitely many points in, like intervals in the real line, bounded intervals in the real line have got infinitely many points in, so they don't count as finite subsets. So again, make sure that you know the definition of finite. Finite means you can, it's empty, or you can write the elements in a finite list. If you count the empty list as a finite list, then the empty set counts for that reason. So the empty set has no points in it. So in notation, if you use this to mean the number of points in a set, oh, perhaps that'd be, let's not risk that. That was used in one of the modules last year. But so number of points in the empty set is 0, which counts as a finite number. I won't bother to write that down. So empty set does count as a finite set. That's a special case, and we'll come back to that in a minute. So see below for a bit more on that. But otherwise, a typical finite set has the form x1, x2, up to some xn, and you stop, containing r to the d. And I'll leave it as an exercise to prove that that must be closed. Now, again, there's going to be more information coming up in a bit that shows that if you take a union of finitely many closed sets, you get a closed set. So in fact, it's enough to deal with one point. If you take a set with one point in it and prove that that gives you a closed set, then you can get the rest by taking finite unions, or you can do it directly, or you can just have a look at it, see how there can't possibly be any non-interior points in the complement. But I'll leave that to you to think about. But again, it's a standard fact you can quote unless you're asked to prove it. Finite sets are closed is standard, but if somebody says, proves that finite sets are closed, you can't say because finite sets are closed. And here's the special case I mentioned. This is something strange because these sets are both open. So we saw earlier that we saw that the empty set and r to the d are open in r to the d. So it sounds very strange to say now that they're closed, especially if you think that closed means not open. But closed doesn't mean not open. Closed means that the complement is open. So let's have a look at these. So let's set A to be the empty set, then A complement is equal to r to the d, which is open in r to the d. Thus, A is closed in r to the d. And similarly, without bothering to name a letter, the complement of r to the d is the empty set, which is open in r to the d. So r to the d is closed in r to the d. Okay, so let me ask, are there any questions on those examples so far? I hope that I've made it very clear that closed sets, closed does not mean the same as not open. So far we've seen some examples of sets which are open and not closed. Some examples of sets which are closed and not open. Some examples of sets which are both open and closed. But we haven't finished all the possibilities yet. In fact, most sets are neither. So most sets are neither open nor closed. Now, one thing you could do is to take a half-open interval in the real line. Hold on, let's do that in a different colour. If that's A, this is A complement. Oops, that's red. Here, A is a half-open interval 0, 1. It's neither open nor closed, and neither is its complement. So neither A nor A complement is open. So neither A nor A complement is closed. In fact, more logical to say neither A complement nor A is closed. But that at least you could call half open. But most sets aren't even intervals, and you can't even describe them as half open or anything like that. Q and Q complement are even worse, in some sense. Well, I say even worse, but they certainly do the job of being neither open nor closed. They're also not intervals. And it doesn't make sense to describe them as half open or anything like that. Q and Q complement, you're not even going to be able to sketch properly, except as lots of dots on the line. Some sets are both open and closed. Well, we've seen that. We know that the empty set and R to the D are both open and closed in R to the D. Sets like that are called clopen. Sounds like a joke, but actually it is used in the literature. And it's certainly, some people say open hyphen closed. That's too boring. I like clopen. So I didn't invent that one. So, or you could say open closed if you're boring. There aren't very many, but it's not easy to prove. In fact, in R to the D, it's different when you come to metric and topological spaces in third year. But in R to the D, it turns out those are the only two clopen sets. So this is a tricky exercise, or a rather tricky exercise, or look in the books. These are the only clopen subsets. Now, you're allowed to, actually, you can quote that fact. If you know that fact, that they're the only clopen subsets of R to the D, I will let you quote that as long as you really do tell me. If you want to use that fact, that can help you show a set. You see, usually, if you're trying to show a set is not open, you should be looking for non-interior points. If you're trying to show a set is not closed, you should be looking at the complement and trying to check whether or not it's open. But if it so happens you've shown a set is open and you want to argue it's not closed, you could quote this fact to help. Say, I've shown it is open, I quote this standard fact, and since my set isn't empty and it isn't R to the D, and it is open, that proves it can't be closed. Not because closed means not open, which it doesn't, but because of this standard but tricky fact that you ought to quote. Now, if you want to know more about that, it's under the topic connectedness, which you'll find in the level 3 module, metric and topological spaces, where you look at those spaces which do fall into two pieces or more, and those which don't. So it's very important that you know the difference between closed and not open. I said enough about that today. I hope I made it very clear. Now, you can use properties of open sets to prove quite a lot of things about closed sets. let me remind you of De Morgan's laws. The complement of a union is the intersection of the complements. And the complement of an intersection is the union of the complements, which is this one. And you can do this for infinite unions and intersections as well, which you can also find on a question sheet somewhere. If you take a union of infinitely many sets and take the complement, that's still the same as the intersection of all the complements of the sets. And similarly, if you take the intersection of infinitely many sets and then take the complement of that, you get the union of the complements of those sets. And that's on one of the question sheets. So now, you can prove things about closed sets using standard facts about open sets. And this is proof by definition, or possibly you can even call it proof by De Morgan. You take the facts about open sets and you take complements everywhere and see what you get. So here's a result you should know about closed sets, but the proof is not examinable as bookwork. If you are asked it, it'll be in a non-bookwork part of an exam question. So, because complement swaps intersection and union, and complement swaps closed sets and open sets, it swaps the results. Remember, you could take a union of infinitely many open sets and be open. Well, because of what complement does, that means you could take an intersection of infinitely many closed sets and still be closed. Whereas, you could take an intersection of finitely many open sets and still be open. Well, for closed sets, complement turns intersection to union. So, so you can take a union of finitely many closed sets and still be closed, but you can't necessarily take a union of infinitely many closed sets. A union of infinitely many closed sets may not be closed anymore. And one way to see that is with the rational numbers. The rational numbers, for those of you who know about countable sets, can be written as an infinite list of points. Now, every point gives you, every single point set is a closed set. Take that union, you get all the rational numbers, and the rational numbers gives you a set which is neither open nor closed. So that's one particularly horrible example of something which is a union of a sequence of closed sets, and yet it's one of the nastiest sets you're going to meet in this module. So again, something strange happens in the limit. But you're all right for finite or countable intersections, and indeed you can take uncountable intersections as well. When you do metric and topological spaces, there's nothing wrong with intersecting uncountably many closed sets, and it's still going to be closed. Doesn't matter how many you intersect, it's still closed. But for unions, you're only safe if you take a union of finitely many closed sets. And that brings us to the end of chapter 4. Are there any final questions on this introductory chapter on the topology of R2D and closed sets? If not, oh yes, no. Yes, was there a question over here? No? Okay. Then I'll pause the recording and we'll start chapter 5.